Chapter 5, Think and Explain. So, number 34, identify in each of the following interactions the action and reaction force. Again, not fond of the term reaction as talked about in a previous video as well as in class, but action reaction is basically he's asking about the pair of forces. So a hammer hits a nail. The hammer exerts a force on the nail exerts a force on the hammer. Those forces are equal in magnitude, opposite in direction. Earth gravity pulling down on a book. It's gravitational force pulling down on the book. So if the Earth pulls down on the book with a gravitational force, the book pulls up on the Earth with the same magnitude of gravitational force, whatever the weight of the book is, assuming the book is near the surface of the Earth. And a helicopter pushes down air downwards. This is why helicopters fly, because the blades push the air downwards, and therefore the air pushes the blade upwards. And since the blade's attached to the helicopter rises. Number 35, we have Steve and Gretchen embracing, sort of. Looks like they're posing for the camera. But the question is Gretchen touching the dad or dad touching her? They are touching each other. It's impossible for it to be one way. And this is also just Newton's third law for if A exerts a force on B, B exerts the same magnitude of force, the same type of force on A. And that's it. 36, when you rub your hands together, can you push harder on one hand than the other? And no, not the way that's intended. That, we're talking about the hands pushing on each other like this. And so they will push with the equal amount of force on each other. I don't think he's intending that you're, going to be exerting some other force on the hand outside. Or that you're pushing on a force so that the hand goes, like that. 37, you hold an apple over your head, identify all the forces. So if you're holding the apple over their head, it depends on if you're holding it by the stem or if you're holding it in the palm of your hand. So if it's in the palm of your hand, you have the force of gravity down, normal force up. If you're holding it by the stem, you've got force of gravity acting down, and then you've got presumably friction acting up on it. And they talk about the reaction forces. So if we go to the holding in the palm of your hand, the Earth pulls the apple down, the apple pulls up on the Earth. Your hand pushes with a normal force up on the apple pushes down on your hand. And that's what you're feeling. You're feeling the normal force of the apple pushing down on your hand. When you drop the apple, suddenly the normal force goes away. The only force acting on it is the force of gravity. We're ignoring air resistance, of course. And yeah, as they say, ignore air drag. And so you have the apple falling, being pulled by the gravitational force down. So the gravitational force from the Earth is acting down on the apple, and therefore you flip the objects in the direction. The apple is pulling up on the Earth with the gravitational force. Number 43, you exert a horizontal force of 200 newtons to slide a crate across a factory floor at a constant velocity. How much friction is exerted by the floor on the crate? So if it's a constant velocity, that means the change in velocity is 0, means acceleration is 0, means the total force is 0. Equilibrium. So if it's an equilibrium, if you're pushing 200 newtons of force this way, there has to be 200 newtons of force pushing in the other direction. And so presumably that's friction as opposed to there's someone else involved. And so it's 200 newtons of force. Is the friction equal and oppositely directed to your 200 newton push? It is, but in the last one, if it's not the reaction force to your push, what is? It is not the reaction force. It is not, Newton's third law is not saying if I push 200 newtons of force on an object this way, that the friction will be 200 that way. It just so happens that it's 200 that way because you're pushing it at a constant velocity. If I'm pushing on the crate 200 newtons that way, the crate pushes on me 200 newtons in the other direction. So, and if the ground is pushing with 200 newtons of force this way on the crate exerts a 200 newton force that way on the ground. And so those are the action-reaction pairs. Number 49, strongman will push the two initially stationary freight cars of equal mass apart before he drops straight to the ground. Is it possible for him to give either car a greater speed than the other? If he's dropping straight to the ground, that means that the forces acting on him are balanced out so that there's no horizontal acceleration. So if he's, I'm assuming that initially stationary freight cars. So the freight cars are right here. Straight cars are right here. He's pushing in between. And so because he drops straight down, the forces acting on him are balanced, and therefore he is pushing with the same magnitude of force on the two cars. If the cars are equal mass, which they are, then same force, same mass, same acceleration, the cars will go the same. 50. It is possible, by the way, it is possible for him to exert more force on one cart than the other. If that's the case, then the forces on him will be unbalanced, and he will not drop straight to the ground, but he will accelerate, and he will basically, it's a parabolic, it's projectile motion. He'll go in a parabola. Number 50. Suppose two carts, one twice as massive as the other, fly apart when compressed spring that joins them is released. What is the acceleration of the heavier cart relative to the lighter? It's the same force on both, and so if you double the mass of one cart, it's going to be half the acceleration. So the heavier one, the one that's twice as massive, which is better wording than heavier, the one that's twice as massive will move with half the acceleration. And the reason why I corrected about massive versus heavier is if it's on Earth, yeah, you can get away with that. But if they're in outer space, the heavier doesn't really make a lot of sense there. And so, but the acceleration will still work the same. So the more massive car will have half the acceleration. 55. Your instructor challenges you and your friend to each pull on a pair of scales attached to the end of a horizontal rope in a tug-of-war fashion, so that the readings on the scales will differ. Can this be done? No, they can't. Assuming it's an ideal rope, then the tension at the two ends of the rope are going to be the same. And so the tension that 1/4 scale exerts on the rope will be the same amount of tension on the other end of the rope and that scale. And so the two scales will read the same thing. Number 60. There are two interactions that involve a stone at rest on the ground. One is between the stone and the earth as a whole. Earth pulls down on the stone. And in parentheses it says mg, that's not milligrams, that's mass times acceleration due to gravity. And the stone pulls up on the earth. What is the other interaction? So they talked about the gravitational pull, but there's also that support force, what we call in class normal force, or what a lot of textbooks call normal force. So the normal force is pushing up on the rock is pushing down on the ground. 60. A stone is at rest on the ground. A vector shows a weight of the stone. Complete the vector diagram. So we've done that in class. It's basically box on ground is the one that we did, except this time it's rock on ground. And the conventional name of the vector that you have drawn, presumably he drew a weight vector on it. That is the force that is acting on the rock itself. That's not the force acting on the ground. He did not separate the diagrams to make it very clear. And then the other force, the normal force acting up. Normal force. 62. A stone is suspended at rest by a string. Draw the forces vectors of all the forces acting on the stone. Again, you have force acting down, and then there's tension acting up. Now, you do actually see how the rope is attached to the stone. And so we do have this issue with, is that tension or is that a normal force? Because you've got the string is wrapped around the rock. And so there is actually a normal force from the string. You can get away with, in this case, of just calling it a tension acting up and just sort of lumping the whole thing together, because there might be some friction in there too. It's hard to tell, so we'll just call it tension acting up on the rock. There's obviously tension acting down on the rope at where the rock is, so we got rock, tension acting up, tension acting down on the rope. At the other end of the rope, when it's attached to the ceiling, there's a tension acting up on the rope, down on the ceiling. 63. Same stone is being accelerated vertically. Draw the force vectors. The forces acting on the rock are the same. The only difference is the tension acting up on the rock is greater than the weight of the rock. Because it's accelerating upwards, therefore the force upwards has to be greater than the force downwards. Suppose the string in the preceding exercise breaks and the stone slows in its upward motion. Draw the force diagram and the stone would reach the top of the peak. Well, once the string breaks, assuming that the string is close enough to massless, once the string breaks, the only force acting on it is the force of gravity. And so that's going to be, so it's going to slow down, it's going to stop, and then it's going to start plummeting back down. Force of gravity is the only force acting on it. 65. What is the acceleration of the stone of the preceding question at the top of the path? Well, it's the acceleration due to gravity, because the only force on it is the force due to gravity. 66. Here the stone is sliding down a free, friction-free incline. So they have the rock sort of rounded, but it could just be a box. If it's friction-free, there's no rolling involved. It's just sliding down. Identify the forces acting on it. Well, it's friction-free, so you have weight acting down, and then there's going to be a normal force acting up at an angle, or depends on the way you're looking at the problem. There's a perpendicular to the ramp acting away from the ramp is the normal force. If you add them together, those two vectors, so you have one at an angle and one that's straight down, if you add them together, they will produce a vector. So think from my knuckle to the tip of this finger here, it will produce a vector that is directly parallel with the ramp. So 67, the stone is at rest interacting with the surface and the block. Identify the forces acting on the stone. So when you've got you got a block here and you got a rock sitting on top of it, and then you got an incline. So basically you have a normal force acting perpendicular to the incline. You have weight acting down, and then there's a normal force from the block acting up the ramp. And so you have three forces acting on the rock. They'll end up being three forces acting on the block. One, the normal force from the rock is acting down the ramp. The normal force from the ramp is acting perpendicular to the ramp, and up and to the right if you're looking at the picture. And then there's the force of gravity acting down. And that is the Think and Explains. Yes, Think and Explains.